Welcome back, guys, to another episode of Next Gen VR. In this video, I want to discuss wireless PCVR technologies that can achieve low latency streaming. So first, I will go over the introduction, then provide a summary of the technologies, the ongoing research that I found, and evaluation and analysis of the results, and my conclusion. So first, the introduction. Why is low latency wireless PCVR important? Well, there are a lot of benefits to cutting the umbilical cord. The first is much greater freedom of movement. When you aren't tied down by that cable, you can jump, you can run around without any worries. It also increases immersion in the virtual environment when you're no longer reminded that you're in the real world by this tether. Third is the elimination of any tripping hazards. And fourth is better portability, because anyone who owns a Quest 2 will tell you that they really like that it's untethered headset. So first, let's go over how wireless VR works. So first, the VR headset captures the user's head motion with a built-in inertial measurement unit called IMU. Data transfer is bidirectional, meaning the host's rendered VR image frames are sent to headset via downlink, and then the IMU motion data is sent back to the headset via uplink. New VR frames are rendered based on that motion data. So there are two categories of VR headsets, standalone and tethered, and the focus of my research is on the tethered side. But first, I will go over the most popular standalone headsets. We have the Oculus Quest 2 for consumers. We have the Vive Focus 3 for business, and the Vive Flow miniaturized headset dedicated for niche consumers. The most popular tethered VR headsets are the Valve Index, released a long time ago. The HP Reverb G2, Pimax 8KX, and Vario Aro are recent headsets with a pretty high and impressive resolution and refresh rate, which is why for wireless to be achieved in tethered, you would need very high bandwidth and low latency. So the benefits of PCVR over standalone is that we have much higher quality of VR games, much better graphics, and much better performance. Compared to Quest 2 games, the quality of PCVR games is unparalleled. So current wireless PCVR solutions are inadequate. We have Wi-Fi streaming, but the problems with that are high latency, lower image quality due to compression because of the lower bandwidth capabilities, and just overall performance issues that result in motion sickness and juddering. Next, we have the WeGig Vive wireless adapter, which was introduced a few years ago, but it's exclusive to Vive Pro 1 and 2 headset series, and it's limited to 3264 x 1632 resolution at 90 Hz, meaning it's not really going to support future VR headsets and even current VR headsets. So now I'm going to go over the summary of the technologies that I found. So, the potential technologies for achieving low latency wireless VR include the following: WeGig 2, 5G plus edge computing, 6G terahertz, laser beam transmission, and Li-Fi. So for WeGig 2, the development began in 2015 and was finally approved in March of 2021. It is a new standard called the IEEE 802.11.AY, and the previous standard was AD, which was WeGig 1. It runs on the millimeter wave electromagnetic spectrum. It has a much higher frequency of 60 gigahertz, but the downside is it has shorter range than Wi-Fi. It has an ultra-fast 100 gigabytes per second transmission speed, very high bandwidth. However, it is vulnerable to signal blockage, including objects and environment, so the signal does not travel through walls. It can be blocked by other objects in the room. But however, this line of sight problem is minimized using beamform reflection techniques, and unlike WeGig 1, WeGig 2 introduces MIMO channels, multiple input and multiple output, to have the 4 times the throughput of WeGig 1. So it uses 4 2.16 gigahertz channels for a total of 8.64 gigahertz. Next, we have 5G plus edge computing. It is 100 times faster than previous cellular technology and runs in the 3.3 gigahertz to 4.2 gigahertz millimeter wave spectrum. It has a very high bandwidth and only 1 millisecond latency compared to 20 milliseconds in previous technology. So you could download a movie ultra fast in this mode. And then edge computing servers are placed near the user to minimize latency and congestion. So the idea is having it close to the users allows for shorter distance of transmission. So here are some diagrams. So on the left, you will see the idea of the public and private cloud and the core 5G network. And then we have multi-access edge computers in the cell towers, which are close to the end users. So you will need a lot of MEC servers in order to cover a wide network due to the short range of 5G. On the right, we have a diagram that I took from a screen grab. This is HTC Vive presenting their private 5G plus edge computing solution, where they achieved a 15 millisecond round trip time from 6 miles away on a Lumen Edge host. And yeah, they have a pretty impressive result for that. Next is the 6G terahertz network. This is in a very early stage of development compared to 5G. It also runs on the millimeter wave spectrum. However, the possible bands can range from 100 gigahertz to 3 terahertz. It has not been finalized yet as a standard. It has higher bandwidth than 5G, but even shorter range than 5G. Next is laser beam transmission. It uses free space optical communication. This is a technology that's been around since the 1960s. An example of such is a remote control that uses infrared light to communicate with a television screen. So infrared light is invisible to the naked eye, but it can transmit gigabytes per second of data, depending on the type of laser. It has very high bandwidth, low latency, but it is line of sight dependent. Next, we have Li-Fi. This transmits data through light bulb light waves. 100 gigabytes per second transmission speed. The bulbs have already been installed in the Paris subway system for wireless internet access. It uses visible light, which is 10,000 times larger capacity than the radio wave spectrum. It has low installation costs. It is more secure than Wi-Fi since a light signal cannot be intercepted as easily as radio. And it is not necessarily line of sight dependent, so it can be installed in existing light bulbs, and wherever the light is beamed, it will cover that whole area, so it's not a specific direction. So now we'll go over some ongoing research into low latency wireless VR technologies. So first thing I discovered was a paper called Extended Reality over 5G and 5G Advanced New Radio. You can go to my slides and click the link if you would like to read any of these papers. So it was published in March 2022. New VR headsets are needed improvements in power consumption, performance, and heat management for 5G. VR is delay sensitive, meaning any packet that's delayed is lost. So VR in that sense has a 10 millisecond latency requirement, quite low. The standardization of 5G is still being worked on, but flexible duplexing could allow for simultaneous downlink and uplink transmission, which would be a huge boost for the VR use case. So next we have enhancing next generation extended reality applications with coded caching. So this was published in February 2022, and it proposes multi-antenna coded caching for high transmission, low latency communication. Now, mmWave suffers from instability and signal blockage, so what it attempts to do is address wireless bottlenecks by using the cache storage that's stored throughout the 5G network. So the way it works is it splits popular VR content into fragments, and it allows for the exclusion of fragments that a user doesn't need when they call on that cache. The only downside with this is a fairness issue, since the user with the lowest signal decoding speed reduces the speed of everyone else. They propose a solution of increasing cache size for lower signal users and other methods. Now, they're still working on a framework for implementation, so since this is a relatively new study, they're still working on that. Next paper I found is 6G. Terahertz Reconfigurable Intelligent Surfaces, RISs, for 6G communication, published in February as well. RISs are basically programmable structures that can control the direction of electromagnetic waves, meaning it can be highly directional data transfer, allowing for better range. Next, we have basically a machine learning allocation model for solving the unreliable terahertz RIS issue. So this was published in March. So it proposes our reinforcement learning to improve reliability by switching channels whenever it detects an RIS failure. And VR over this framework has not been studied previously. Next, another discovery was by a Chinese company. They achieved 6G breakthrough in January 2022, where they had 206.25 gigabytes per second transmission speed in a 6G chip, 10 to 20 times faster than 5G, but they have a long way to go before commercial 6G, which is estimated to be in 2028. Next, we have China launches world's first 6G satellite. This happened in November 2020. And in related news that I found, Huawei plans to launch its own 6G satellites in the near future, and it has a goal of a 6G network by 2030. So you can see a screen grab of the satellite from the video. And next, we have other areas of research. So another way to improve wireless VR is to reduce the amount of data transfer that needs to be transferred wirelessly. So dynamic foveated rendering uses eye tracking to sample a higher resolution in the area of the eye's focus and lower resolution in the periphery. This allows to save on rendering. Foveated transport uses eye tracking for split GPU rendering, which is somewhat different. And display stream compression is an algorithm for lossless compression that reduces bandwidth. So now on to evaluation and analysis. So here I made a comparison chart of the many different technologies, and I will go over them now. So Wi-Fi has medium bandwidth. It does not require line of sight. It has medium range, but a medium latency, low cost, local network size, and a low feasibility. You cannot transfer large amounts of data that are needed for wireless low latency PCVR. Now, we have WeGig, which was an older technology now. WeGig 2, 5G, 6G, laser beams, Wi-Fi, all very high bandwidth, all of them short range, ultra low latency, and the costs vary. 5G and 6G have a wide area network. And the most feasible, in my belief, is WeGig 2, followed by laser beams, and then 5G and Wi-Fi are other possible solutions. So the most feasible options, WeGig 2, laser beam transmission. So a WeGig module is planning to be featured in an upcoming VR headset called the Pimax 12K QLED, a release date of Q4 2022. The WeGig module promises 6K resolution per eye and 90 Hz refresh rate. So you can see in this diagram, the 60 gigahertz WeGig will go to the Pimax engine using dynamic foveated rendering. So it is the belief that it'll probably use WeGig 2 since the resolution and refresh rate demands are unprecedented compared to previous releases. So the pros of WeGig 2, we have a high bandwidth over 4 channels, fast transmission speed, minimal compression, and bidirectional data transfer supported. But as a short transmission distance, if you go beyond 5 meters or so, it's vulnerable to signal blockage and it has a high battery consumption. So here is Unlink VR's laser beam solution. It uses a transmitter and a receiver installed on the headset. The goal is to be compatible with any VR headset, and it tracks the user as their head moves around. It can use reflectors installed on the ceiling for better line of sight improvement. So this is similar to how beamforming is used in WeGig 2, except this is using laser beams. So here's a demonstration of how it tracks the movement, and it is pretty impressive. They use visible light so that it's for demonstration purposes, but normally be invisible. So laser beam transmission has 40 times the speed of Wi-Fi, ultra low latency, and can use reflectors and mirrors to improve line of sight. However, it's still mostly line of sight dependent. It takes some time to recover tracking if lost. The data goes in only one direction from PC to headset, meaning it will need to use Wi-Fi to receive motion data from the headset, so it's not bidirectional. Fortunately, though, motion data from headset requires much less speed and bandwidth than the downlink, and it's estimated to cost between $700 to $900. So some possible near future solutions are definitely these technologies, but it will take years to build out the 5G network before we get ubiquitous range everywhere in the continent. 6G has even shorter range, much farther away, but promises even better performance. And Li-Fi needs to be made compatible with more devices before we can see it rolling out more widely. So here's my conclusion. So WeGig 2 is the most feasible solution due to its high bandwidth, low latency, and affordable price. Laser beams could be a good alternative if line of sight ends up being as good as in WeGig 2. 5G still suffers from range issues and will need further building out of the network. It is feasible, however, for private businesses that want to use private 5G. 6G is far away but shows lots of promising developments. And Li-Fi is very low cost and easy to implement, but there's a long way to go for compatibility. So that's it for my video, guys. Thanks for watching. If you enjoyed it, don't forget to hit the like button and subscribe for many more videos about the latest and greatest VR headsets and news.